everyone present over here. Today, I welcome you all on behalf of Parul University. Today, we have Dr. Shekhar Singh Negi with us, and he will going to deliver us a talk regarding dynamical equation on time scale. And he is pursuing his postdoctoral from Umea University, Sweden. He has completed his PhD in Mathematical Science, Indian Institute of Technology, Mandi, Himachal Pradesh. He has published 7 research papers in SCI Impact Factor journals. 4 research papers are under reviewed, and he has many more achievements. So, without wasting our time, let's begin with our talk. So, I invite Dr. Shekhar to deliver his talk. Shekhar.
Okay, thank you. Thank you, Panchal. Am I audible?
Yes, you are audible.
Okay, thank you. Yeah, I hope it is visible to all of you.
Yes, it's visible.
Yeah, okay. So, so good morning, everyone. So, no, not a good morning. So, good afternoon, everyone. So, this is my topic, dynamic equation time scale. So, today I'm going to talk on that topic. So, but before going to start that topic, this talk, I would like to thanks Dr. Jitendra Kumar. So, for this webinar. Okay. And now, so yeah, this is so today I'm going to talk on the some new kind of theory, so which is known as the timescale theory. So I have used that theory in my previous research work in my PhD, and I have done my some papers. So I have done my PhD from IT Mandi, Indian Institute of Technology, Mandi, under the supervision of Dr. Syed Abbas and co-guide Dr. Muslim Malik. And recently I have joined that institute, Umia University, and Department of Computing Science, and I'm working on non-additive measures and integrals. Okay, and working with this Professor Vicentora. Yeah, so these presentations follow some order. So first of all, I would like to discuss about some motivation thoughts behind the timescale theory, and I will also present some you can say that application this application of this theory, this timescale theory. And now then the some preliminaries on time scale will also be there. So I will going to discuss some operators, some which have been a crucial role in the study of the time scale, and some classification of the points will also be discussed, and their graphical interpretation I will also present their graphical interpretations, representations. And now, so this third one is the main definition, main motive of this presentation actually. So which unifies uh, both continuous and discrete calculus. So it will be presented here in section 3. And so for the more convenience, I will also present some example which I'm going to discuss these operators, classification points, and the Hilger derivatives. So I will give and some examples corresponding to that things. And now in the fifth section, I'm going to discuss about the some unifications, because by dint of using that theory, I'm going to discuss about the some unification of equations. So equations means I'm talking about the equations of differential equation and the difference equation. Okay, so here we will discuss about some unification of both calculus. And in the sixth section, in the last section, I'm going to present some few papers, some basic papers actually, basic papers and the basic book of this theory. So from where you can get that book, get the all the things from that book. Okay. Now, so yeah, so motivation. So in 1937, a professor E.T. Bell has their concern. So concern towards the harmonizations of continuous and discrete calculus. And he has also imposed some. He has also proposed some idea that is that possible to include them in one comparison mathematics or not. So after that, in 1988, a German mathematician, Stephen Hilger, has first introduced a timescale theory. So the main motive of this theory is to unify both continuous and discrete calculus. Okay, so now, so this theory is important because it avoids the double analysis and it provides a single theory of many calculus, discrete, continuous, and so on. And yeah, so today this theory has taken a gain shape actually, and it has many applications. You can see it has many applications like in biotechnology, population dynamics, economics, quantum physics, electric circuit, and the social sciences, etc. So in particular, because I have worked over that population dynamics, so I can show you some details about this application of about the population dynamics. So you can see here, yeah, yeah. So here I have considered some pictures. So it's nothing but it is a some special kind of species. So the first one is a 13 escada, and which is known as the Floridian brood. And the second one, this is a similar kind of species, which is a 17 escada, which is also known as the Frasicada. So we call it 13 year and 17 year because it lives as a larva 13 or 17 year, but as adult 2 or 3 days, maybe perhaps 7 days. So so in order to analysis of this type of species, so if I know about the some analysis or and know about their dynamic changes in their lifespan, so what we do, I just make a model corresponding to that species. So if my model consists only the differential equation or difference equation, so from both of them we cannot able to get the accurate development of this type of species because their lifespans contains continuous and discrete as well. Okay, so in order to analysis the to get the accurate development of this species, what I do, I have to just consider. I need to know about the some kind of theory which unify both continuous and discrete calculus at the same time. Okay, so that is possible only on the you can say that in a time scale theory. Yeah, so from here you can see in this picture you can also see here in the 1 to 8 picture represent how the species come out from its egg and leave its egg. From here you can see that leave its egg before it die, and the process will go on. So here we can see that their lifespan will represent like that union. This black line will represent when they live, and this gap represent when they die. Okay, and before it die it leaves an egg, so again he lives 7 days and die. So the process will be go like that. So so in order to analyze that type span, that type of is behavior like the span of this species, we need we need that theory, so that is more capable to analysis of that species. Okay, and now, yeah, so these are the some application of of this theory. Now, yeah, so in mathematically we can say that a time scale is nothing but a non-empty closed subset of a real number R. And throughout this presentation, this is a standard notation I'm using here, this T. Okay, this will be represented as a time scale. So if I'm going to say that this set is going to be if I'm saying that this is a time scale, so that means it means that it should be the non-empty and the closed subset of a real number. That should be the part of my real number, and provided it should be non-empty and closed. Okay, so for example we can also see here yeah, yeah, so these are the some example of the time scale. So as we know that the set of all real number itself a closed non-empty closed subset of a real number R. So it will be the time scale. It can be the time scale, and the set of all natural number and set of all integer. All these are the time scale, and the closed interval as we know that, and the Cantor set. These are this is also the closed non-empty closed subset of a real number R. So this will also be the time scale. And the set of harmonic numbers, later I will discuss about what is the harmonic number. It's a collection of the sequences. Okay, and yeah, so this kind of set is also a non-empty closed subset because 0 is a limit point of that set, so it is included. I'm including this 0 is here, so this is a scattered points, means discrete points we have, and this is a 0 is a dense point, so limit point is there. So we can say that this can be denoted by the time scale T, so because it is a non-empty closed subset of a real number R. Okay, so we can also find some other kind of, apart from that one, we can also discuss, we can also find and construct some kind of time scale. Okay, so these are the some examples, some trivial examples. Yeah, so this is the yeah, so here I'm going to discuss about the some operators, so which have been a crucial role in the study of the time scale. Okay, and yeah, this theory, if you are going to study that time scale, so you should also know about that operator actually. Okay, so yeah, so yeah, this is the forward jump operator and the backward jump operator and the greatness operator. So I'm going to go in detail about this operator. So yeah, so you can see here the forward jump operator, it is like it is mapped from t to t such that sigma t is represented as the infimum of all the set which consists the element like this s, that should be the element of my time scale. Okay, but it should satisfy like this one. So what does it mean? It means that we are just taking this sigma t is just representing my next element. That's why we are calling it the forward jump operator. Isn't it? So what does it mean? Forward jump operator means sigma t means it is just next. If you are considering a time scale like integers, later I will also discuss that things. If you consider 1 2 3 4 5 6 7 8 9 10 elements, if I'm picking 1 point, suppose I'm taking 7, so what will be my next element? Next element will be my 8. So what does that mean? So 7 is my t, so this is my 7 is t, my sigma t is, means sigma 7 is next element, which is 8. Okay, so that is the some representation of that forward jump operator. Okay, by the similar argument we can also impose over that backward jump operator. So it will just give you, suppose you have a point 1 2 3 4 and you are just considering 2 points. Okay, and this is a backward jump operator, it will gives you at a point 2, it will gives you 1. So row of 2, it will be just previous element, which is 1, because you have considered the time scale 1 2 3 4. Either you can consider this, you can also consider the smooth line. Okay, so later I will discuss that things also. Yeah, so this is the forward jump operator and this is the backward jump operator. We know about that one. And what is the greatness operator? So greatness operator is mapped from mu t to this one. So this is which should be the positive and which represent like this one. So what does that mean? So here you can see that mu t is nothing but sigma t minus t. What does it mean? It means that sigma t, I know that this is my forward jump operator. Okay, it means that it is just next element of t. So just next, I'm talking about just next. So it means that this is just next minus that point. So what does it mean? It represent this is always positive. So it satisfies that things is satisfied because it maps to t to this positive. So this must be positive. And this is forward minus t at point t. So what does it mean? It means that it represents the difference between the two consecutive points of the time scale. Are you getting my point? So this represent greatness nothing but it represent the difference between the two consecutive points of the time scale. Okay, so now the question, here the question arises that is this operator, means I'm talking about all these operators, the forward jump operator, backward jump operator, and the greatness operator. So what does it mean? Can I say that this is well defined? Because if your function operator map is well defined, then you can talk about something. Okay, so is it operator, this operator is going to be well defined? Is it well defined? No, I must say that it is not. Why it is not? So in general it is not true actually. So I can also take some particular example. Let us say, yeah, so here you can see the two pictures. So this is not a red line, blue line. Okay, so this is we have the time scale t, and another we have a time scale, because I know that my sigma is mapping from time scale to time scale, and in my domains I am considering my time scale with the 3 points, this blue and this red. 3 points are there, and again this empty, this is this 3 points are there, because the t has only the 3 points. You can also make an order 1 2 3, it will be considered 1 2 3. Okay, so this is it has some gap. I'm just considering some particular time scale. So I'm just going to show that it is it is not defined. It is not well defined actually. I'm just going to prove that. So I have considered that one. So you can also assume that 1 2 3 and 1 2 3. So as we know that my sigma t is represent, it is nothing but the forward jump operator. It gives you the next element. So what does that mean? So if I'm operating my sigma over there, so what I get? I just get the next element, not that one. I get that point, isn't it? So sigma, this blue point will represent like this one. Sigma of this blue point will be represent like this. Now what about this one? If I'm operating my sigma over there, so what I get nothing, isn't it? So what does that mean? So it is not defined actually. Okay, so in order to define that thing, that you can say that operator, we need to consider some substitution. Okay, we should have some substitution. My substitution will be nothing but what I do, I just take a sigma of red is nothing but this blue, means like this one. Now this time this is well defined. Okay, because I have every point of this domain, it will map somewhere in the codomain. Okay, so it means that this is well defined. But after substitution, I have substitute that one at the end of this point, means infimum of phi, because I'm getting phi. Infimum phi means infimum of empty set will nothing but supremum of this t, because this is the end element. That should be the supremum. Why I'm taking supremum? Because supremum always exists. Sometimes we may have the maximum. If I'm talking about the maximum and I'm taking the dense point, so we cannot get the maximum point if we have an open and union, something like. So I'm just taking the supremum here. So how can I define this? So I have to just consider, I have to just substitute my infimum of empty set is nothing but supremum of t, means t means time scale. So then in that case, it will be the well defined. Okay, so I can move back to the previous. Yeah, so this is well defined over that one, that means that substitution. So my substitution will be like this one. So if I'm substitute my infimum of phi empty set, infimum means sigma of t, because we are not able to get the next element. So infimum of phi will be supremum of t if I'm taking like this. And for the backward, if I'm taking supremum of phi empty set is equal to infimum of t. So that it has some sense. Okay, so this operator has some sense for this operator. So we can talk about their one onto differentiability, continuity, and so on. Okay, now we can proceed for the further study. So this is well defined. Now this is a well defined we have done. Okay, now the second question is arise that is it monotonic? Yeah, this is monotonic. Because why it is monotonic? Because I know that my sigma t is forward jump operator. It gives you this next element. It means that it is going high, isn't it? So it is well defined. Okay, so yeah, so this is yes. So it is monotonically increasing. Sigma is monotonically increasing, and my rho is monotonically decreasing. So if we have a is less than equal to b, then I can say that sigma of a less than equal to sigma of b. I can easily by the definition I can get that relation, sigma a less than equal to sigma b. And similar things I can impose over there over this rho, and that will become this rho is nothing but the monotonically decreasing. Okay, now my next question here. So we have the well defined, and this is monotonic. We know that about this operator, these operators. Okay, now the second third question here, is it continuous or not? So we cannot think about that one, because we have some arbitrary collection of the time scale. So but I must say that it is not actually, because we may have some different kind of sets. Okay, so in which they may be the continuous or discontinuous. So but in general it is not continuous. So how we can say that? Yeah. Yeah. So this is it continuous? No. How? Yeah, this one. So here I have considered this type of time scale because this is my domain, this is my codomain. Okay, so my codomain should be the, yeah, it should be the time scale. So this is not a smooth. Yeah, so we have -1. This is a time scale -1 by n. So it consists the discrete points. Okay, and because I need to my time scale should be the non-empty closed subset. So because this is discrete, it has some limit point. So limit point is 0. So that 0 should be there. So I have just included here union with 0. Yeah, union with 0 and 1 and 2. So these are the some isolate points are there. This is the dense and this is isolate points, isn't it? So can I check that my sigma is continuous or not? Yeah, I can check, easily check. So suppose I'm picking one point here, yeah, like this one. So this is a problem point. So I'm picking that point 0. So I'm just going to check at that point, is it continuous or not? Okay, so what theory I will use here? So I am just using, suppose you have a function which is a real valued function you have, and it is continuous. So what does that mean? It is continuous if and only if you must have in a sequence an which is converse to a, at which you are going to check that it is continuous or not. Okay, so an going to be converse to a at as n tending to infinity, then my function f of an is should be converse to f of a. Then you can say that this is continuous. Okay, this is a simple definition of check the, you can check the continuity of this function. Okay, so I will using that concept here. So sigma, I'm going to check that sigma is going to continuous or continuous at that point 0 or not. So what I do, I have just picking that point. So -1 by n, this is the point of this my time scale. So I can easily take that sequence. So -1 by n is my an that converts to 0. This is okay. What about my sigma -1 by n? Is it converts to sigma 0? It is not. Why it is not? Yeah, you can see here. Sigma -1 by n, you can just take the next element, then my next element will be like this. But when I'm taking my n larger, sufficient large, then it will goes to 0. So it means that my sigma -1 n, this sequence will goes to 0, isn't it? But my, if I'm going if I'm say that this is continuous, so it means that my sigma -1 should be converse to sigma 0, but it is going to be 0, and this sigma 0 is nothing but 1 because it gives you the next element. Sigma 0, it gives you the next element, it is 1. So 0 cannot be equal to 1, isn't it? So it means that this is this for this type of time scale, it is in general, you can say that in general sigma is not continuous. Okay, so in general it is not continuous, but later I will tell you all these things when this sigma is continuous, at which point it is not. Okay, so later I will discuss. I will also show you some books in which they have given that type of concept. Okay, so from this picture we can conclude, we easily conclude that we may have some kind of time scale at which my sigma is not continuous. Okay, so from this picture I can say that in general it is not continuous. So this is well defined. Okay, this one yeah, we have already done that one. So well defined, yeah, with the substitution, and this is monotonically increasing, monotonically decreasing. I'm talking about the forward jump operator, backward jump operator respectively. Okay, and this is continuous. No, it is not. We have done that one. Yeah, so now what about the 1 1 and on 2? Yeah, so what can you say about the, is it 1 1 or on 2? Yeah, no, we cannot say that. In general we cannot say, because we have some arbitrary collection of sets, because time scale that should be the closed non-empty, so it may be anything. Okay, so in general it is not. So how can we do that? How can we see that, say that, yeah, this is no. Yeah, so the same picture you can, when we have defined the time scale is sigma is well defined or not, we can say that we can take the that example we can take. So this is a time scale which consists of 3 points which has some order like 1 2 3, like 3 4 7 9 8 and 9 10 11. Okay, you can make an order. So this is an order 3 points, this is an order in 3 points. So Now, so I am going to check that my sigma is onto 1 1 or not. So here this picture easily shows you. So that cannot be onto, because if you are saying that it is onto, so it means it should, you should have a point in a codomain that should have a preimage. So that doesn't gives you, okay, that is not allowing to say that it is onto. So it means that it is not onto. Sigma, in general, sigma is not onto, isn't it? And from these 2 points we can say that it is not 1 1, because you know that, so that if you are taking that 2 different points in the domain, so if you map over these 2 points, that map should be different. Okay, if it is unique like that one, that, so it cannot. So it means that it is neither onto nor 1 1. So in general it is not 1 1 and onto. Okay, so we have discussed the well-definedness and monotonicity. We know that about this forward jump operator and backward jump operator, and the continuity. We know that at which point it is. Yeah, there is some problem at the continuity of my sigma, and as well as the rho. And the 1 1 on 2, we know that it is not. In general, it is not. Okay, so these are some basic concept about the forward jump operator. Okay, so because this is important if you are going to study the time scale. Yeah, so next one I'm going to discuss about some classifications. Classification means you have a time scale. It has time scale means non-empty closed subset of a real number that can be anything. Okay, so it means that it can be anything. It means that every element, every set consists some different kinds of elements. So how can we define, how can we classify that points? So it can be classified like that. So suppose we have a time scale. So this is t. So arbitrary. I'm talking about the arbitrary time scale. We have t. So small. Suppose I'm taking a small point t from this time scale, picking one point, random point. So that will be called the right scatter. Okay, right scattered means there is some gap between that point and the next point. So that will call the right, from the right. I'm talking about right. Okay, so that will call the right scattered. So in mathematically, you can write that one. So t is less than sigma t. I know that my sigma t is forward jump operator. Okay, it gives you the next element of t. So t less than sigma t. It means that it has some gap, isn't it? Similarly, we can use for the left scattered. It means that if I'm taking t, it's the left scattered. It means that whatever in my right side, but I don't care about my right side, but it should be, it is right. If you are saying that it is left scattered, it means that there is some gap from the left. Okay, so it means that my rho t less than t, or you can also say that t greater than rho t. Okay, now this is the right dense. So right dense means it is dense from the right. Okay, not left, it is dense from the right. So it means that right gives you this sigma t. So then it means that t equal to sigma t, isn't it? So if you have like that one, so you can say that right dense. So but my t cannot be the supreme of t. As you know that we have just substitute that value, so we cannot talk about there that point, because that gives you that endpoint also gives you the same, t is equal to sigma t. So I'm not interested to taking like supreme t. Okay, so because I have imposed some conditions in the endpoint of this time scale. Okay, so I'm just removing that points. I'm not considering that points to define the right dense. Okay, so this is the right dense. It should be satisfied that relation t should be equal to sigma t. Then we can say that this is right dense. Similarly, I can say that this is left dense if t is equal to rho t. Okay, so these are the points. So with the help of that that classification, we can easily define the isolate. I know that this is isolate. Isolate means it is isolate somewhere, so there is nobody is near about around that point. So it means that t is, because we are in a real line, so t, we have a t. If I'm going to say that it is isolate, it means that there is no dense point from the left and right. It means that there is some gap. The next element and the previous element has some gap. So it will be represented like mathematically, you can say right like that. So rho t less than t less than sigma t. Okay, and similarly dense if it is dense from the both side, left and right, isn't it? So it is dense, that will be called dense. So you cannot find some difference between the 2 points, between the next and the previous point at that point t. Okay, so we can also see some graphical representations of that point, so which is yeah, this one. So now in the first picture, in this picture, in the first one I have considered the real line. So real line, you can say that this is dense points. So every point is a dense point. Means suppose I'm picking one point here, so it will be dense from the both side, left and right. So it is dense. Okay, and if I'm considering the integer points, so I know that integer points are some well ordered. Okay, well ordered, I'm talking about some step size. It has some step size, so it has one gap. So these are the isolate points. All the points are isolate. Okay, so this is also the time scale. This one is also time scale r, and this is integer, this is also time scale. So if I'm picking that points, any point random, I can say I can pick. So if I'm picking that point, so that point, this is a random because arbitrary point I'm taking. So this point is isolate point, so it is scattered left and right, scattered at the same time. So this will be called the, you can say that isolate points collections. Okay, now as yeah, so we have also some different kind of we may have also some different kind of, you can say that time scale, means collection of non-empty collection, non-empty subset of real number, like this one. So it is nothing but the union of the close intervals, isn't it? So that this is some special kind of time scale, which because it consists all the type of points like this one. So all the type of points, base points, so it is consisting like all the points of this. So I will tell you here. Yeah, so if I'm talking about these points between this smooth line, so it is dense, isn't it? And if I'm talking about this end point of this first interval, so it is left dense and right scattered at the same time. Okay, so this point is left dense from the left, and scattered from the right at the same time. And this is, we have the point, this is left scattered and right dense at the same time. So it is consisting all that points except the isolate points. Okay, and yeah, so this is some special kind of time scale. So I have also discussed that type of that kind of set in the application of you can say that in the application of the time scale, so in the previous slide. Okay, so yeah, and we also know that the Cantor set, how we define the Cantor set. So we know that. So I'm not going to discuss that one. So, but this Cantor set is also the closed, non-empty closed subset of a real number. So that's why we can also call it as a time scale. Okay. So yeah, this is a time scale. So we can also discuss about the set. We can also use that set, that kind of set in the time scale theory. Yeah, and so yeah, this one is I was talking about that harmonic numbers. So harmonic numbers means we have some, this is also the isolate points actually. So we have h1 is nothing but 1, sorry, 1, yeah, 1. And h2 means we have another point is 1 plus 1 by 2, it is 3 by 2 something, and so on. So it is some collection of that points. Okay, and apart from this, we may have, we can also deal with that type of points. So it is you can say that somewhere it is dense from the left, right scattered at the same time, and isolate points, this is the isolate points we have. And yeah, so yeah, some gap is different from that set. And so it means that we can also discuss from the some random points, but provided that that should be the non-empty closed subset of the real number R. So then we can discuss that type of set in the time scale theory. Okay, so this is the way to define the time scale. Okay, in graphically. So yeah, this is important actually. So you should know about that if you are going to study that this time scale theory later. I will tell you. So my derivative will depends on this type of time scale, this type of points actually. Okay, so you cannot take a derivative as it is. So as we use in usual derivative, so that doesn't happen in this derivative actually. So we have to just careful about that point. We should know about that points, okay, how it is behaving and how it is look like. Okay, so yeah, so next one I am just going to discuss the derivative, so which depends on that time, that points. Okay, so now, so up to now we have discussed the some applications and application of time scale. We know that, so my motivations, okay, and yeah, so and the some operators which is frequently used in this theory of time scale. So you should know about that. So we have already done that part. So I know that what is my forward jump operator, backward jump operator, and gradients operator, and we also know about the some classification of the points time scale. So now we turn to define the definition of Hilger derivatives. So yeah, this one. So this is the definition, the main definition of this presentation, actually. So here you have a function which map from the t to r. So t is a time scale, isn't it? So the definition of derivative, you can say the derivative on time scale, either you can say that Hilger derivative, or you can say that the delta derivative, because it is represented by that delta. So all the names are same. Okay. So this the main motive of this theory, this derivative is to unify the all derivatives, derivative of continuous and discrete. Okay, once for the differential equation and the other for difference equation I'm talking about. Are you getting my point? So yeah, this is the time scale. Suppose I'm taking the smooth point, I'm talking about the smooth point. So what happens with this derivative? It will goes to, so that whole thing will become the usual derivative. So you can also denote by this one, this one, by f delta t is nothing but f prime, which is f dash. So because we have a dense point, so it is coincide with the usual derivative. Okay, now if I am going to take that my t is isolate points, what does it mean? It means that you are talking about the forward difference formula. Yes, I'm talking about that one. So that definition, that things will be going to change to forward difference formula. So that will gives you the forward difference formula. Okay, so that definition will coincide with the forward difference formula. Okay, so not only these two kind of points you can discuss with this derivative, but you can also take some different kind of, because we have already discussed in the previous slide. So we have some different kind of points, so we can also discuss that the derivative, that we can also find some derivative of that type of points which we have discussed in the previous slide, isn't it? So this is the more general definition of derivatives, you can say that. Okay, so you can also, with the help of that, once you can also make an model which make a model of the species, that species which we have discussed in the first slide, in my first slide. So you can also make a model of that species with this derivative, actually, because it suits that derivative suits to that analysis, to that type of species, actually. Okay, you cannot use that derivative model and the discrete model. Okay, so you need such theory which works simultaneously, so that things will helps you to study in the better study you can do with this derivative. Okay, yeah, so yeah, so this is the main this was the main definition, the Hilger derivative. You can also see in the one, so later I will show you that paper and the books, okay, related to this theory. Yeah, so we know about that derivative. Yeah, so in so we know about the Hilger derivative, so we can think about the more about this derivative, so the linearity and some properties of this time scale. Okay, of this derivative, sorry. Yeah, so this one. So as we know that in the usual sense, we know that if I'm going to check that my function is going to be differentiate or not, so first of all you should know about the continuity. So your function should be the continuous. So in this, the similar things happens in this case also. So what is that? So the continuity of my function should be will be is the necessary condition for my delta differentiability. Are you getting my point? So if I'm going to check that my function is going to be differentiable, delta differentiable, not differentiable, this is delta differentiable, because this is more general derivative concept of derivatives. Okay, so if I'm going to check that is it delta differentiable or not, so first of all I need to check that my function is going to be continuous or not. Okay, so if it is continuous, then I can think about the derivative. I'm not sure that it is exist or not, but it gives you something or not, but because this is a necessary condition for this delta derivative. So then we should first of all we should check that it is continuous or not. So then we can proceed for the delta differentiability of that function, timescale function. Okay, this one. And as I already told you that you have a function continuous, because this is necessary condition for that differentiability. And if you have a continuous function and t is a right scattered point, you have a point t and next point has some gap. Okay, between these 2 points has some gap. So that gap represent that mu t. So this is nothing but the forward difference formula. This next element minus t ft, and this is mu t. In particular, you can also think, you can also see suppose you have a you can say that integers points you have. So it has some you can say that the difference between the two consecutive points is fixed. Fixed means this is 1 because you have considered integer. Okay, so you have an integer, so that will be ft plus 1 minus ft by 1. So it is nothing but the forward difference formula. Okay, so that the derivative, the previous derivative, will coincide with the forward difference formula with this point if you have a t right scatter points. Okay, we don't care about the previous point. It may be dense or it may be scattered. Okay, but if you have a t is right scattered, by this definition we have that things which is nothing but the forward difference formula. Okay, now come to the next one. So this is we have the t right dense. Right dense means there is no, you are not able to get the difference. You are not able to find the some epsilon, so that my right side is empty. Okay, so you cannot do that. So it means that this is a right dense you have. Okay, so t is equal to sigma t. So in that case, that differential will coincide with your usual derivative. Okay, usual derivative means you have that derivative usual. This is f delta is nothing but ft. Okay, yeah. So that should be provided, that should be satisfied the that should be exist and the finite. Okay, yeah. So we can move to next one. Yeah, so this is the property. So these are some properties, that some linearity is there and dilations are there, and product of the two delta differential function. We know that in the usual sense it is represented like that, except because you are working over the in some kind of new theory, which is timescale theories. But in this case, their expression will be quite similar, but it has some changes there. But there is a sigma t. So if you take the t equals to r, that will coincide with your usual derivative, because this is sigma t will be t. So gt ft f dash plus g dash ft. Okay, so this will be happening like that. So you have that one. So product of two delta differential function will be can be represented as follows, like this one. The representation will be like this. And now we can also discuss about some the fractions. So we can also differentiate that one. So provided that because I know that in order to validate that one, so that should be the non-zero. So if you have that one, this is non-zero at that 2 points. So we can find that this fractional part is going to be different, delta differentiable, not differentiable. This is a more general delta differentiable at that point, and their expression will be like that, like this one. So it is also means it will also coincide with your previous usual derivative when you take the t equals to r. Okay, so that will be nothing but that expression will be nothing but like this. And yeah, so for more general we can also discuss about the derivative of the two composition, derivative of the two delta differentiable of two composition of two functions, which is f and g. So you should have that point. So my function is not basically my function is not going to be I'm not taking this function as a, you can say that on the time scale. Okay, so that should be the continuously differentiable, means you should have a function that should be continuous and the derivative should be continuous. So if you have that one, but my g should be the delta differentiable. Okay, so that their expression will be like this one. So if you take t equals to r, then it will coincide with your usual composition derivative, means g dash f dash g dash. Okay, So it will be like this one. So it will be easily can be easily found that it coincide with the uh, dense sense. I mean, if you consider this smooth sense, okay, so it will be coincide. Yeah. Now, so yeah, so this is important. So actually, so we should know about that one. So because we often use that things actually. Yeah. Now, so here I have I'm just going to discuss about some particular example of this. So for the better understanding of this derivative, I have put some example and their corresponding delta derivatives like this one. So you can see here. So this is function. This is a time scale function. I have considered here t square. So you don't see this one. So if I'm differentiating that one, so what I get, I just get 2t, isn't it? This is 2t. So in the usual sense, it is 2t. And so uh, if we have a isolates points, suppose I'm considering the integers. Okay, natural number, we can also consider natural number. So it has a step size 1. So if I'm going to check that the delta derivative means I'm talking about the forward difference formula of t square at the with step size 1. Okay, so what we get, this is t plus 1 square minus t square. So if we solve that one, we get 2t plus 1, isn't it? So but in this theory, if you know about the delta differentiable, if you know about the time scale theory, you can use that theory and get that expression. So that expression concise, you can say that unify, that harmonize all the concept of continuous and discrete derivatives. Okay, so here directly you will have in the delta derivative you will have like this one, t plus sigma t. Okay, now here you are free to choose any time scale. So suppose you are taking t equal to r, so it will be my sigma t will be t, so that is 2t. So we can that coincide. So because if I'm going to check that it is differentiable, yeah, this is continuous, and if I'm going to check that the value of this derivative, this is 2t, so it will coincide with this. Okay, so similarly if you take the t equals to z, so as you know that this give you the forward difference formula. By the forward difference formula of this t square will be nothing but 2t plus 1. So this 2t plus 1 can also be obtained from that derivative. Okay, so this is better actually because it gives you the various theory in a single theory. Are you getting my point? So this is the the enhanced beauty of this theory actually. Okay, so yeah, so you can also take some another example, sigma t, and where t is positive because that should be the well defined. So it is I'm taking here the positive. So this is positive. You have their corresponding delta derivative will be like this, 1 by root t plus root sigma t. Okay, so and so on. You can see that this is the corresponding. These are the examples and their corresponding. You can say that delta derivative. Okay, so in particular I can also show you some I can also elaborate that some one of the example. So suppose I'm taking the a power t. This is I'm considering because my a is positive here, and at means this is ft equal to at. So that is, yeah, you can also take a as you can also replace a by e. So et, this is exponential function like this one. Okay, so their expression like this one. Okay, but I'm not going through that one, so I'm just take the particular example, particular things. I'm just going to check that how it behaving. Okay, so yeah, I will also use that one. So okay, so yeah, so this is a way to see this particular example. So you have the function ft to r, where ft equals to at, where a is positive here. Now my f delta t will be like this one because this value is depends on my domain. Are you getting my point? So if you differentiate that one, so you will easily get that one. In the usual sense, you have that one. Okay, so you have that one, so it can be obtained from your journal derivative. I already discussed with you. Yeah, this one, journal derivative means, yeah, from you can also get from this relation. Okay, this is nothing but f delta t. So yeah, so it can be get from this one. So and if you going to check the usual sense, you can your result will be coincide with this value. Okay, so when I'm taking t equals to r, it has values that this one. If I'm taking if I'm going to take t equals to z, means isolates points I'm talking about, so that will be that by the forward difference formula, for the forward difference formula, I can easily get that one. And if I'm increasing my step size, I'm taking the arbitrary step size, which is h is positive, so it may be anything 2 3 4 5 2.7 8.9, any step size I'm taking here. So corresponding to that time scale, it will be expressed like that: at bracket ah minus 1 by h. So that this h is my step size. Okay, so it is also work on this type of space, this type of time scale. And suppose I'm considering some kind of time scale which consists the isolates points as well as the dense points. So as you can see here that this is a dense point and this is a isolates points, so it is that derivative is also possible in the time scale, and their expression will be like this, isn't it? So this is the expression of this derivative. And you can also take like this type of point, and we can also differentiate uh, we can also think about the some kind of union of closed intervals. Okay, so this represent the smooth, this represent the isolates. Right means I'm talking about the right scattered. So corresponding to right scattered we have like this, and corresponding to the smooth we should have this one, isn't it? So and so on. You can also you can also consider the Cantor set. So because I know that Cantor set also a non-empty closed set of a real number r, so that can be denoted by the t, so that can be considered as a t time scale. So over that point, over that that kind of time scale, you can also discuss about their derivative too. Okay, so and so on. So you can also take some different kind of time scale, provided that should be the non-empty closed set of a real number. Okay, so if it is, then you can think about their derivative. Okay, not only these two, you can also think about that derivatives of that that type kind of points. Okay, so this is the way to see the how it is going to be different from the usual derivative. Okay, so you can see that one. Yeah, so this is the, so you can also check that exponential at and sine t function has expression like this one, and if you differentiate that one, you know that this is nothing but cos t, isn't it? So if you differentiate that one, this is cos t, but in the delta derivative it will express like this one. So if you take t equals to r, it will be cos t. Okay, it should be cos t. Yeah, you can get that one. You can get the cos t. Okay, so you will have that cos t if you take the f delta t equals to r here, and so on. So you can also do that. You can also check is it how their expression. Okay, with over the different time scales. Yeah, so these are the some examples. So this is it will be good if you go through that so this is a good way to understand that derivative actually. Okay, and yeah, so now here I'm going to discuss about the some unification. Now here I'm just going to discuss about the unification of the equation. Equation means my equation is going to consist derivative as well as the as well as the you can say that the corresponding discrete version derivative. Okay, so I'm just going to club all these things into the one equation. Okay, so by using the time scale. Okay, so here you can see that in the first one I have considered the ordinary differential equation, you know, that initial value problem. So that expression like this one, so lambda is constant here, my yt is unknown function is here, and my t is coming from my time scale, not time scale, so just not consider that one. So my t is coming from my r, just take as r, and this is my one is a initial value, and this is the initial point here. Okay, so I know that the what is the solution of that one, so I'm not going through the detail to solve that one. So I know that we also know that what is the solution of that one, that thing. So yeah, this is the solution. So if you can put over there, so you can easily find that satisfies that one. Okay, so yeah, so this is the solution of that corresponding that ordinary differential equation initial value problem. And if we can also consider the consider some kind of, you can say that discrete version of their corresponding discrete version of that initial value problem, so which is like this. So as you know that in the discrete we have to just take like delta by t, means forward difference formula, because it has a step size which fixed is a step size here. So with this the all are the same, so that but the structure is different but theme is same here. So this is the initial value problem in the discrete sense. So it has expression like this one, the solution will be like this. We know that. So if you're going to solve that one, so you will definitely get that one. So that things is going to be you can also check that it is satisfying or not. So it must be satisfied, that one. So it is a solution of that one. So yeah, so if I'm going to if I'm able to check that t equals to z, so I can also check when t equals to 2z, because it is here I have just increasing my step size. So it is 2. If it is 2, start from 2, so do 0 2 4 6 and so on. Is something like that on n negative part also. So their corresponding solution will be like this one, and their corresponding difference formula will be difference equation will be like this one. Okay, and this 2 represent the step size. Okay, so there should be the 1, but I forgot to write here. So this is 2 represent the step size 2. So we can also think about the more actually. So I am just taking the t equals to z. Okay, h equals to z. So I'm taking here h is positive, so it's step size h. So their corresponding solution will be like this one. So it is very difficult to find some so because it consuming time actually. So because if I so first of all you have this one, so you have to check that what is the solution of that one. So you just gone through the some procedure and get that relation, and similarly you will also do by this one. But if you have a time scale, so you can club all this all these equations and make a one equation, make a one equation which consists all these equations with their corresponding solutions, if you know about the time scale theory, because we know that. Okay, so with the help of the time scale theory we can harmonize, or you can say that we can unify this all these equations into the one bucket. Okay, so that bucket will be the time scale. So that is, yeah, this is the dynamic equation on the time scale we have. So my dynamic equation or time scale expression, the equation expressions will be like this: f delta t equal to lambda by t, and y t naught equal to 1. This is my initial point, and this is initial value at the point t naught. Okay, so and their corresponding solution, because I know that how to deal with the how to work over the time scale. So I can easily get that relation. We can easily actually this results you can find in the one of the paper I will show you later. Okay, so that, yeah, so this is, we have the expression. So this is nothing but the solution of that dynamic equation on time scale. Okay, provided that should be satisfied, that one, because this is the conditions. We know that sometimes we have to restrict our we restrict our domain and function and so on. Okay, so provided if we have that relation, and then it has that expression has the solution like this one, so that will call the dynamic equation on the time scale. So from here I can easily get that if I'm going to take my time scale is smooth, t equals to r, then I can easily get that with the help of that one. So if I'm putting t equals to r here, so that will coincide with that whole thing. You getting my point? So when t equals to r, that dynamic equation time scale is nothing but the initial value problem. So as we already discussed here, so that one with their solution too. Okay, so we don't need to check all these things and not gone through all these things if you know about this time scale, dynamic equation time scale. So that this is the more general time scale. This is the more general equations I must say here. So this is a more general which consists all this type of equations. Not only this one, we can also proceed for the further. You can say that yeah. So from here we can also deal with the some different kind of sets. Okay, not only the isolates and dense point. We can also discuss with the solution and the corresponding dynamic equation over some kind of what we call it is uh, as a union of the closed intervals and counter set. We can also discuss about that. For the counter set, suppose you are taking t equals to c means counter set. So if it is satisfying that one, so you can easily get that the the equations over the counter set domain counter set having the solution this one. Okay, the structure may be some different, but that will be the solution of that equation. So this is the more general thing we have discussed here. Okay, yeah. So yeah, so this is the way to define. So because this is an exponential function actually, so this is the exponential function that can be written in that way. Okay, so this is the more general exponential function in the theory of the time scale. So yeah, so this is the exponential function. So it will also coincide when you take t equals to r. So yeah, t equals to r means I'm talking about t equals to r means difference between the two consecutive point is zero. So it means that my h is zero. So h is zero is it is gives you z. So it will be like this one. Okay, so you can conclude from this. Yeah. So these are the some references actually. I just want to share with you. So this is the time scale. So this is the first paper. This is the first theory actually which have been established and introduced. You can say that by the Hilger in their paper in 1989. That is 1990. So it has been submitted in 1989. So yeah. Yeah, so this is so I can also show you that their results. So they have put it some excellent results actually. Yeah, so I hope you are able to see that one. Yeah, so it has been published in the Results in Mathematics, so in 1990, and this is the paper in which the author have discussed they have introduced the timescale theory actually. So you can see from here. Yeah, so these they have started from the uh, difference formula and their corresponding continuous version, and at the end they have he has just club these things into the one theory which is known as the right now it is known as the timescale theory. Okay, with this preliminaries actually. So they have just proved that things, then some special tool, you can say that some necessary tools for this theory they have established here. So yeah, yeah, he has given some many results he has given here. So it's a 29 pages paper, so you can read that one. So I will just show you some main result here. uh, yeah, so muti yeah, this one. So you can see here. uh, I don't know you are able to see or not. Yeah, so I'm just making zoom. Okay, yeah. So this is the dynamical triple and the notion of the differential equation. So they have given the uh, uh, derivative. We have already discussed that one. So this is the definition of delta derivative, Hilger derivative. So yeah, so which unifies both the derivatives actually, all kind of derivative which we have discussed in the previous slide. Okay, so this is the way to define my delta derivative. Okay, so our delta derivative. Yeah, so these are the some property we have already discussed that things. Okay, so if you are interested to see then I will send this paper and this slide to this paper to Jitender, so you can take from him. Yeah, so yeah, these are the there are so many results actually you can find here. Yeah, these are the here they have discussed the Cauchy integral formula. So these are the fundamental results for the calculus actually. So they have also given he has also given that result in their paper. So this is actually the good paper. So dynamic equation for this they have also considered that, and he has also discussed their solutions too. Yeah, so yeah, so he has discussed like this one, and he has also given some unique solution for the simple dynamic equation time scale. So which I have already discussed with you. Yeah, yeah, uh, linear equation. I don't know where it is. Yeah, you can find from this paper. Okay, so yeah, so here they have also he has also discussed about the RD continuous, and you can say that in order to define the, you can say that the pre-additive, what we call it, antiderivative. So we need to know about the RD continuous and what we call it, RD continuous, and we should know about the difference between the RD continuous and regulated points, regulated functions, and the continuous functions. So if you know about that, then you can easily understand that things. So yeah, This is the this author have discussed here in this paper. Yeah, and for the more if you want to study that the theory and in more detail, so we have also two books actually. So this is the advanced. I'm not going through the right now. I'm not going through that one. So because in this paper they have in this you can say that in this book they have the author have discussed their some kind of measures, Riemann integral, Lebesgue integral, or some kind of integrals they have discussed in this paper. So this is a some kind of you can say that advanced. But if you are going through the basic concept of this dynamic equation time scale, so you can go through that book actually. So I would prefer that book to you. Yeah. So yeah. So this is a dynamic equation on time scale which have been published in 2000. I don't know 2000, 2001, maybe around. And these are some well-known author Martin Bonner and Alan Peterson. So yeah, so you can find many things, some basic things about the time scale. Okay, so yeah, this is we have. Yeah, so you can in the first chapter you can find the time scale about the some basic definitions, some examples, and some integrations, chain rules, and polynomials for the basic results you can find from this one. And they have also given some references, so you can also go through that way. So for the better understanding, they have given some uh, they have defined the some easiest way actually. So this is book is quite better to study if you are beginner. So you can must go with this book actually. And then they have also extend their theory to the first order and then the second order wrong scan they have also used, and so on. They have also extend for the measure chains. Okay, and yeah, so somewhere they have also used some kind, you can say that Riccati transformation. So basically the Riccati, yeah, so dynamic equation, yeah, so this one, dynamic inequality is also important because whenever you going to study said some theory, so you should have somewhere you have to deal with the inequality. So that inequality can be get from that chapter 6. Okay, and yeah, so yeah. So yeah, I am not going through the whole paper, but I can show you. Yeah, this one we have discussed. Uh, yeah, this one scattered classification of points, and yeah. So yeah, these are some properties of time scale, and yeah. So yeah, so they have also given in this books you also find some examples, some many examples, you can say that some application of this time scale. So in electric circuit they have also given some kind of application of this that theory actually. So it has a broad theory actually, broad application in this theory. And yeah, so this is, yeah, you can also see that this is the characters that they have discussed in detail. So if you are interested to read, then you can go through that book actually. So you can see uh, some results about the counter sites. And yeah, so yeah, there are so many results actually. So it will be better to go download this book and check everyone. Okay. So now, so I'm just going to finish that this talk. So I hope you have enjoyed. Yeah, so I'm just going to finish this talk here. Yeah, so
Okay,
thank you.
so thank you
Thank you
so
so
much,
much.
sir, for your valuable time as well as
Yeah, yeah,
sharing your wonderful, informative lectures.
yeah. If you have any
Okay, is
question,
there
so
any doubt from all?
yeah,
Yes.
yeah, yeah.
Is there any doubt?
Yeah, if you have any question, doubt, yeah, so we can discuss. Maybe we can also discuss later. So it is not necessary.
Okay, actually, sir, I have one doubt.
Uh, yeah, yeah.
As we have discussed
Don't call me
about the
sir.
delta
We are
derivative.
friends actually. Why you are calling me
Hello.
sir? Are you getting me? Uh,
So I have one question that is
yeah,
we have discussed about delta derivative.
yeah,
So
yeah, yeah, delta derivative.
uh, can we define nebula derivative in the same way?
Yeah, yeah, yeah. We can do that. Yeah, you. Why we can do?
Okay.
Do you have a book that one?
Yes, I have book.
Yeah, so you just see that one. So they have also discussed that nabla. So because through this presentation I have just used the forward difference formula, so I have just discussed about the forward. So you can also, the same things you can also impose for the nabla. Okay, that will give, provides you the from backward. So it will go up, it will go back. So there may be the expression may be some difference you may find. Suppose so yeah, in the forward difference formula, in the here we use mu t equals to sigma t minus t, because this represent the gap. Okay, so in that case we have a nu which represent t minus rho t. So that is also represent the difference between the two consecutive bonds or time scale. So you can also use that. That's it. So that will also gives you the same thing which we have discussed for the uh, forward. Are you getting my point, Jitendra?
Yes,
I think
I'm
my
getting that point.
network is slow. Yeah. Okay, okay.
Okay, and we can, if we are going to take time scale as a set of real numbers, so we can extend our time scale to the ordinary derivative, right?
Yeah, yeah, yeah. That can be. You can do
Okay. So whatever the applications are there, we can extend that application to time scale also, and whatever
time
the
scale.
applications are there for time scale, we can extend to real number also.
Real number. Yeah, yeah, yeah. You can do. Yeah, yeah.
So
Okay.
any other question? Okay, so now no more questions. So I would like to thanks to you
Uh,
for sparing your valuable time,
yeah. Thank you so
particularly in
much.
these days.
Yeah. Yeah.
Okay, so
Okay.
now,
So yeah. Thank you
and
so
I
much,
will
Jeet. So
thank
I
you.
will catch you on WhatsApp.
Okay,
Okay. Thank you. Bye.
bye.
So thank you to all of you.